John Levesque here again. In this video, we are going to be introducing OpenMP directives into Leslie 3D. Leslie 3D is the application we worked with in the previous video on the memory analysis tool. We are going to be using perftools-lite-loops and reveal in this video. Okay, the first thing we want to do is load perftools-lite-loops. File is Joel, and now we do a make. Now notice that during the compile, the compiler warns us that OpenMP directives will be ignored. That is because that the profile loops only works on applications running unthreaded, and so we get that warning. Okay. So at the end of this, it's actually creating the instrument and executable. And now let's qsub. Now in this, I am going to be running this on 8 nodes, 8 MPI tasks. So because we're not doing OpenMP. And the other thing is I want to get the loop lengths that are going to be maximum. In other words, the MPI will not be dividing up the loops. Okay. Let's see what the output is doing. Now this is going to be relatively slow because it's really only using 8 cores. Okay, so finally got this thing to run. It actually took quite a bit longer because it's only running on 8 cores. It took 5 minutes. But here, and of course I've covered this on earlier videos on using this, but notice that what we have is we have several very meaty loops in these flux routines. And for example, in flux K on line 29, this in the average min max loop iteration count is pretty good on 28. So what we're going to do is look at reveal and look at this particular loop. First have to generate the program library. So I'm going to go into my make file, and notice in my make file that I have, I'm going to use whole program analysis. That's what the HWP is. And I'm going to generate a program library called leslie3d.pl. So I will write that. I'll do a make clean. Now, one of the things that the make clean does is it removes this program library, because you always want to start from scratch with generating this program library. Now we'll do a make. Okay, once the make is done, we're going to invoke reveal again, this time with the program library. Right? And so what we come up with is the program view where we have all of the routines. Now what we're interested in, if we go back to the loop statistics, is that flux K loop on line 28. Okay, so we're going to go into flux K. And if I click on that, it gives me all the routines that are on flux K. Now I want to come over here And I want to go down to line 28. All right, so 28 is the outermost of this double nested loop. This F means that it's flattened. In other words, all the routines that have been called in this have been inlined. Here are the loops in flux K, and the V says that this was vectorized. A D means that this was deleted. It recognized that in scheme was not equal to 2, so it didn't generate code for this. All right, now what I want to do is I'm going to right click on this and I'm going to say scope loop. Okay. So I have one loop selected and now I'm going to start scoping. And this is something that we can ignore. In fact, let's say this. Okay, so it says scoping is completed. Notice the red dots. This is saying that this is not automatically parallelized. So we look at the scoping results. And here are the things that are of concern with reveal. First, we have FSK. If we click on FSK, then that is highlighted over in this window. We don't really see, here we go. Now, this is a very difficult analysis by the compiler. Basically, this is an array that is independent of J. And the problem is that these are called array constants. And in order to make sure that this does not have loop carried dependencies, you have to be assured that all of the uses of FSK are covered by sets. In other words, if you use an element in FSK, it better be set that iteration in the loop, because you want the thread that's going to use it to have it. And that is hard for the compiler to really grasp. And so it's saying it doesn't like that. Now, unfortunately, these scoping results went away. Now, in order to assure the compiler that this is not an issue, I'm going to click on this. And a drop-down menu comes and I choose private. Okay. Now, what it's warning me about is that, okay, if this is a private array, you have to make sure that all the values that are used are set, or else you need first value setting, where the thread 0 copies its copy of FSK to everyone else. Well, that is not needed, so I'm not going to be concerned with that. So that kind of went away now. However, we still have this warning here. Now, this is FSK. That I means down the call chain. And so that also has no issue. So I'm going to make that private. I get this same warning that I ignore. Now, IND it's kind of silly here. I mean, it's used as upper bound of the loop index. I'm not sure why the compiler is having problems with that, but that should be shared. Okay? KC max is exactly the same thing. I actually think this might be a little bit of a bug, but that's easy to say, don't worry about it. We will make this shared as well. Now, L is set each time through the loop and then it's used. So that is in fact going to be private. Now the last one, Q, is here again. It's an array constant that is not dependent upon J. And we have to once again assure that all of the uses are set prior to use in each iteration of the loop. And it is. So I'm going to make that private. Okay, so now all of the concerns, other things have been scoped fine, but those that were a concern I overrode. Now I'm going to insert directives. So now if we go over here, here are the directives that are inserted by Cray Reveal. And so here are the private and shared variables. Okay, so that is our first loop. Now if we go back to this, we see that loop 29 is in this, that's the inner loop from that one. So let's go to flux J and look at line 28. So here we go to flux J, and we're going to go down to, go back to flux J, and we're going to go to loop 28, and we're going to scope the loop. All right, well, this flux K loop has already been scoped, so we're going to turn those off. Okay, so we're going to try to turn these off. Okay, so now we have one loop selected, the one in flux J, so we'll start scoping that. Scoping complete. And now, if we come back here and look at this, here again, in fact, this is almost identical to the one before. They are extremely similar. The analysis is the same. And so basically what we're going to do is make this private, ignore that, make this private, ignore that, make this shared, make this shared, L is the private, and QS is private. Okay, and now we're going to insert directives and close this. Okay, so now we have parallelized the higher level loops in K and J, and now let's go to flux I on line 21. Okay. Okay. And now right click, scope loop. Here again, we want to unmark this. And one loop is selected, so we're going to start scoping. Scoping complete. Go up to loop 21. And now exactly the same thing. So all three of these, same type, they're three different sweeps through the grid. And so the analysis is pretty much all the same. We don't have to really discuss much of that. Once again, the I means down the end line. So there's multiple issues there. Okay. I is unresolved. I is I. This is a bug in the compiler. At least it's a conservative bug. In other words, that should be private. IC max should be shared. L should be private. And QS should be private. Okay. Now, so here again, we insert directives. Okay, so let's stop there. So now what we're going to do is we are going to save all. So all of the files that were modified are flux I, flux J, and flux K. Okay. All right, now, let's now get out. Okay, now what we want to do now is we want to load perftools module. Oh, God. Module load perftools-lite, period. Because we do want to instrument this to see what kind of performance gain we're getting. Okay. And now we want to do a make clean. Now we're going to edit the make file again. And we're not going to use the program library. So all we're going to do is compile it and let perftools-lite do its thing. So now we'll do a make. Okay, now what we're going to do is we're going to edit the run script. Because what I want to do is I'm going to run two situations. This is going to be kind of interesting. The first is we're going to run on all the cores of the two sockets. And we'll make this output a little more appropriate. Okay. And then this will be 16 on 8. Just so we have two different output files here. So this one is going to run with one MPI task on the node and 44 threads across all the nodes. This is going to run with 2 MPI tasks on each node, one on each socket, and then 22 threads on the socket. So we're going to get 2 runs here. So we will, and then we will submit. Okay, so the first execution came back. So let's look at this output file. This is the one using 44 threads. All right. And so it ran 500 cycles. And we see that, in fact, the fluxes are all lower. They used to be up higher. But now these extra routines and update are using most of the time. Okay, and then this is the perftools-lite, so it tells us where in the routine time is being used. But what I want to show you is this memory bandwidth by NUMA node. This is really interesting because we have two sockets, NUMA node 0 and NUMA node 1. Notice that NUMA node 0, the first socket, is primarily using its own data. Okay. Remote memory traffic is low. NUMA node 1 is the second socket, and it is using a lot of memory from NUMA node 0. And this is what I wanted to show. So this is not good at all because it takes a lot longer to get. In fact, look at the memory traffic gigabytes per second for NUMA node 0, where it's using its own data, and NUMA node 1 that's having to get NUMA node 0 data. So you can see that getting data from a different socket, it really degrades things. So now it's going to be kind of interesting to see the performance. Okay, now what we're going to do is look at the second one that had an MPI task on each socket and half the number of threads. Okay, the same thing where in fact the flux routines are running faster, but they're running even faster than when we use 44 threads. Now let's look at this NUMA node stuff. Now look at this. So what you see is the local memory traffic for NUMA node 0 is on its very little going remotely, and NUMA node 1 very little going remotely. So they're both getting the same memory bandwidth from each socket. This is very important when you do OpenMP. Now this video has gone way too long, so the next video we'll get in and parallelize some more of these routines.